In this next section, we're going to discuss solubility. The solubility of a solute is defined as the amount of solute that can dissolve in a certain quantity of solvent. Solubility depends on three things: temperature, the solute's state, so is the solute in solid, liquid, or gas phase, and the solute's affinity for the solvent. We'll talk more about each of these in the slides to come. Let's talk more about how affinity affects solubility. Affinity is a measure of the attraction between the particles of a solute and the particles of a solvent. For example, polar solutes have more affinity for polar solvents than nonpolar solvents. Nonpolar solutes have more affinity to nonpolar solvents than to polar solvents. A way you might have heard this in the past is like dissolves like. So like solutes have an affinity for like solvents, which then increases the solubility. Let's talk about affinity in the real world as it relates to a couple of vitamins, vitamin A and vitamin C. Affinity and molecular structure play an important role in the solubility of several molecular solutes, including vitamins A and C. Vitamin A is not water soluble. Vitamin C is water soluble. Those differences are important to life, and on the next slide, we're going to talk about how we can understand them better just based on their structures. Okay, on the left is vitamin A. It has this long non-polar hydrocarbon chain. If you look at this stick model down here, you can see that it's just carbons and hydrogens, and that's non-polar. So this long non-polar chain that resists interacting with water and is not water soluble. Contrast that with vitamin C on the right. We don't have a long non-polar chain. We have several polar OH groups that can easily hydrogen bond to a polar water molecule, making it water soluble. Solubility is commonly expressed as grams of solute per 100 grams of solvent. You'll often see that. So let's look here at these three different substances. We have methanol, CH3OH. Replace the OH group with chlorine, CH3Cl, and then replace with 4 chlorine, CCl4. What happens to the solubility of each of these substances in water? The first is infinite. The second, very, very small, 0.47, and the last, even less so. Why is that so? Well, water is polar. The more polar the solute, the more affinity it will have for water, so the more readily it will dissolve in water. Keeping that in mind, which of these would be the most polar solute? It would be the first one, because it has the infinite solubility in water, whereas CCl4 is nonpolar and therefore has an extremely small solubility in water, unlike the other two. So this is highly polar, nonpolar, and something in the middle. So you can see the solubility decrease as we go from most polar to least polar. All right, now let's talk about how solubility depends on temperature. The solubility of a solute in a solvent is highly dependent on temperature. In general, solids and liquids dissolve better at higher temperatures. So look what happens as the temperature increases. Look at the solubility of salt, sodium chloride, in water. It increases as the temperature goes up. And I imagine you've had that experience where maybe you're making tea and you want to sweeten it. The sugar will dissolve much more readily in hot tea than it will in already iced tea. Here are three other ways that we describe solutions based on their solubility. The first is unsaturated. So an unsaturated solution contains less than the maximum amount. So if I added more solute, it could be dissolved into the solution. So that's this one here. If I put more of whatever this yellow solute is, it would dissolve in the solution. A saturated solution, so the second one here, contains the maximum amount of dissolved solute that can be stably maintained at that temperature. Often, but not always, precipitate is always present. So if a solution is saturated and you add more, then that more solute is just going to settle to the bottom. It won't dissolve. It'll still be there, but it'll just settle to the bottom of the solution. Finally, a supersaturated solution contains more solute than saturated solution. So the number of molecules dissolved here is more than dissolved here. They're highly unstable, and they quickly transform into a saturated solution if disturbed. So if I have a supersaturated solution, and sometimes all you have to do is like scratch the edge of the inside of this with like a scoop, or add a tiny crystal of solute, whatever it is we are dissolving here. And what rapidly happens is it reverts back to this, where we just have saturated number of particles dissolved, and everything that was extra will settle down to the bottom. In an unsaturated solution, like the one on the left, any additional solute will dissolve. So there's no undissolved solute present as precipitate. In a saturated solution, undissolved solute and dissolved solute are in equilibrium. So there will often be a precipitate present, as the solvent already holds as much solute as it can, so any excess will just exist as precipitate at the bottom. A supersaturated solution is always clear and no precipitant is present, since that would disturb the equilibrium, and excess solute would precipitate, yielding what we've discussed, a saturated solution with a precipitate. Supersaturated solutions can be created by first starting with a solution that is saturated at some initial higher temperature. And then if you slowly cool that solution down so that the amount of solute is above the maximum for that new lower temperature, what you're left with is a supersaturated solution. This is unstable, since if any solid solute is added, the remaining excess solute quickly precipitates out, leaving a saturated solution and precipitant at the bottom. So as we said in the previous slide, this will quickly revert back to this if any sort of disturbance occurs. This series of photos is one of my favorite demonstrations to do, and one of the coolest things you can look up on YouTube. But we have some photos to show you what happens. On the left, this is a supersaturated solution of sodium acetate in water. See, it's clear. We can't see any precipitate here. We might think to our naked eye that this is just a unsaturated or saturated solution. We don't know, right? It's clear without any precipitants. Then a tiny crystal of that sodium acetate is added. So you can just scoop a tiny bit out and drop it in. And that's what happens right here. We drop that tiny crystal, and what happens? It's very unstable, causes all that excess solute to crystallize out of solution. So what we're seeing here is a saturated solution of sodium acetate and the precipitate of excess sodium acetate. Pretty cool. Solubility curves show the amount of solute per fixed amount of solvent dissolved in a saturated solution as a function of temperature. So let's break that down. On the y-axis, we have solubility, which is grams of our solute. In this case, we're talking about potassium nitrate in a fixed amount of solvent in 100 milliliters of water. So what is the solubility of potassium nitrate in 100 milliliters of water at various temperatures? And this fits with the trend we talked about previously, that as the temperature increases, so does the solubility of this solid in water. This solid black line represents the amount of solute necessary for the dissolved and undissolved amounts to be in equilibrium. That's what we would call a saturated solution. Below the line down here would be unsaturated, and above the line would be supersaturated. Solubility curves are difficult to predict for a given ionic salt, okay? They vary widely, and these are just based on, experimental data. So we see in red here the sodium chloride, in this yellowish orange. This increases greatly at high temperatures. This sodium sulfate kind of levels out, and this cesium salt actually decreases with increasing temperature. Okay, so they vary. Let's briefly touch on what happens when we try to dissolve gases in water. So the solubility of gases in water. And the example we talked about previously in this unit was like a carbonated water, a carbonated drink, where we're dissolving the gas in the liquid. So unlike solids, gases become less soluble at higher temperatures. So in general, as the temperature increases, the solubility decreases. The kinetic energy, and therefore the speed of gas molecules, increases with temperature. We know that from our gases unit. At higher temperatures, it's easier for them to break away from their attraction to the solvent and escape the solution. Okay, so as they're moving around faster and have more and more energy, it's actually easier for them to leave the solution than it is for them to stay dissolved in the solution. Here's an example of NH3 ammonia gas dissolved in 100 milliliters of water at different temperatures. So as we go from 0 degrees Celsius up to 100 degrees, look at how much the solubility of that gas decreases. Just like for solids, we can have solubility curves for gases, and they show that inverse relationship of gas solubility and temperature. So you can see for methane, oxygen, carbon monoxide, helium, as temperature increases, solubility decreases. As a result of this relationship, cooler streams, so colder streams of water, have higher dissolved oxygen levels than warmer streams of water, and they therefore support more life because there's more oxygen available. On the other hand, this is also why water that is excessively warmed by either natural or artificial means can lead to damage to marine ecosystems, because the warmer the water is, the less oxygen available for those ecosystems. Gas solubility does not just depend on temperature, it also depends on pressure. The higher the pressure of the gas above the liquid, the greater the solubility of that gas. This is known as Henry's law. Okay, so on the left we have this dynamic equilibrium between dissolved gas in the solution and undissolved gas above the solution. If the pressure on this gas above, you can see there's a water line right here where this exchange is happening. you can see that if the pressure on the undissolved gas above the liquid is increased, so we decrease the volume and increase the pressure here, the equilibrium shifts, and what happens? More of the molecules now are going into the solution. So more gas is dissolved, and then we readjust to a new dynamic equilibrium where the rate of dissolving and undissolving particles is the same. This pressure dynamic is how soft drink manufacturers carbonate soda. They simply raise the pressure of the CO2 above the liquid, causing more of it to dissolve in the liquid. They then seal a lid on the top so the pressure is maintained. The pressure inside of the container is greater than the atmospheric pressure of the surrounding environment or atmosphere, right? So when the container is opened, what happens? The pressure is released. That pressure of the container drops, the equilibrium shifts again, and as a result, now that we have lower pressure, gas comes out of the solution. How do we see that happen? Bubbles are forming in the liquid. Eventually, it will go flat because the bubbles will escape the liquid and enter the surrounding air. Let's look at a mathematical representation of Henry's law. We have this equation that says S1 over P1 equals S2 over P2, where S1 is the solubility of the gas at pressure 1, where pressure 1 is the initial pressure of the gas above the solvent. So if you think back a couple slides, that would be the initial dynamic equilibrium all the way to the left. And then S2 would be the new solubility of the gas at pressure 2, which would be the new pressure of the gas above the solvent. So remember, we pushed that piston down to increase the pressure in that picture a couple slides back. That would be our new P2. And of course, as the pressure increases, we would expect the solubility to also increase. Example 1, Henry's law. When a can of soda is opened, bubbles form as dissolved CO2 comes out of solution due to its reduction in its solubility. In a closed can of soda, so the closed can, CO2 has a partial pressure of 5 atmospheres. Determine the solubility, so we're looking for the solubility at that pressure. So we're looking for solubility at 5 atmospheres. Given that its solubility is 0.1449 grams per 100 milliliters at 1 atmosphere and 25 degrees Celsius. We'll assume a constant temperature. So remember our description of Henry's law, S1 over P1 equals S2 over P2. If we assume that S1 and P1 are the known values for solubility and pressure, then S2 and P2 will involve what we're looking for. What we're looking for is the solubility at 5 atmospheres. So we're looking for S2. So S2 is equal to, we know S1 and P1. So we know the solubility at that first pressure. And then if I just multiply by, let's change colors there. Multiply by P2. All right, so let me set this up and then we'll go ahead to the next slide just to see the answer. So S1 is I wanted to change. S1, 0.1449. P1, 1 atmosphere, times P2, 5 atmospheres. So 0.1449 grams per 100 milliliters times 5 and then divided by 1, just times 5. So let's go to the next slide, just confirm the math there. So 0.1449 grams per 100 milliliters of water times 5 atmospheres over 100, or over 1 atmosphere, excuse me, is 0.7245 grams per 100 milliliters of water. So that's our solubility at that lower, at the higher pressure at 5 atmospheres. Okay, and it makes sense, look how much higher it is, because as the pressure increases, so should the solubility. Example 2, solubility curves. A potassium nitrate solution at 80 degrees Celsius has 75 grams of potassium nitrate in 100 milliliters of water. Is the solution saturated or unsaturated? So the first thing we need to do is just find out where is this intersection of this 80 degrees Celsius and 75 grams. And then we can decide. So 80 degrees Celsius is right here, and if this is 50 and this is 100, 75 will be right halfway in between. Okay. Now, where is that location in reference to this solid black line, this solubility curve? It's below it, so we would call this solution unsaturated. The next slide has a summary of these steps. Find the location on the graph where the solution lies. Compare that to the curve. And again, we did that previously, and we've decided this is an unsaturated solution.